In the last section, we introduced limits, and that was section 2.1. And now we're going to go over section 2.2. We're going to talk about infinite limits and limits at infinity. So the first thing we're going to do is examine the graph of this function here. We have f of x is equal to 1 over 1 minus x. And so this is what the graph looks like. And essentially we see that as x is getting closer and closer to this value 1 from the right, from this direction, we see that the f of x values are getting bigger and bigger, and as we approach x is equal to 1 from the left, these f of x values are getting bigger and bigger, but in the negative direction. And this is shown in these tables here. If we were to plug in values of x here that are getting closer and closer to 1 from the right, we see that our output is getting bigger and bigger, and so what we would say is that the limit of this function as x approaches 1 from the right is equal to infinity. Similarly, if we were to plug in numbers for x that get closer and closer to 1 from the left, we see that these numbers are getting bigger and bigger, negative. So we have really big negative numbers. So this tells us that the limit of our function as x approaches 1 from the left is going to be negative infinity. And so these are infinite limits. All right, now something to note here is that the two-sided limit of this function does not exist as x approaches 1. And this is because neither of the one-sided limits exist. And remember, since the limit from the left is not equal to the limit from the right, the two-sided limit does not exist. And something else to note is that infinity is not an actual number that we can get to in the one-sided limits, so that's why they do not exist. We're just using the infinity symbol to describe what's happening and describe the behavior of these limits. All right. This brings us to the definition of a vertical asymptote. So the vertical line x is equal to a is called a vertical asymptote for our graph if our outputs approach infinity or negative infinity as x approaches this number a from the right or from the left. So in the previous example, x would be equal to 1, so our a would be 1, and that would be our vertical asymptote. Next, we have this theorem here for locating vertical asymptotes of a rational function. So we're told that if we have this function f of x, which is equal to some function n of x over d of x, where for some number c, our denominator d of c is equal to 0 and our numerator is not equal to 0, then the line x is equal to c will be a vertical asymptote of our graph. And so we'll see a few examples of this moving forward, but something to note here is that by theorem 3 in section 2.1, a polynomial function doesn't have any vertical asymptotes. So if you want to go back to section 2.1 and just review that. But something to note here that we know with a rational function there is definitely trouble when there is a zero denominator. So this makes sense. All right, so let's look at an example. We're given this function here, f of x is equal to x minus 3 over x squared minus 4x plus 3. So we have a rational function here. And we want to describe the behavior of our function at each 0 of the denominator. And we'll use our infinity and negative infinity notations here. And we also want to identify all the vertical asymptotes. So the first thing, we want to find when our denominator of our function is 0. But something to note here, if both I'm going to abbreviate numerator as that and denominator as that. So if both our numerator and our denominator are R0, then we have an indeterminate form, right? From last section, we would get indeterminate form, and this means we would have no vertical asymptote. I'm going to abbreviate vertical asymptote with VA. So just something to note here. So the first thing we want to do, again, is find when the denominator is equal to 0. So we can do that by factoring the denominator. We have x squared minus 4x plus 3. And this factors down. We have x here, and multiply to get positive 3, and add to get negative 4. So we have negative 1 and negative 3. So this tells us that our zeros are x is equal to 1 and x is equal to 3. But something to note here, if we were to plug in 3 into our equation, we get our indeterminate form. So this tells us x is equal to 3 is not a vertical asymptote. And then we can conclude, though, that we do have a vertical asymptote at x is equal to 1, because if we were to plug that in to our equation, we would not get our indeterminate form. Okay, so we found our vertical asymptote, and we also want to describe the behavior of our function at these zeros and figure out what's happening as we approach infinity as we approach our vertical asymptote from the left and from the right. So what I'm going to do is make a table how we did in the first example and see what happens when we approach our vertical asymptote 1 from the right. So if we were to plug in 1.1 into our equation, we would get 10. Plugging in 1.01, we would get 100, and then 1.001, we would get 1,000. And if we repeat this, we see that this number is just getting bigger and bigger as we get closer and closer to 1 from the right. So this tells us that the limit of our function, which was as x approaches 1 from the right, is going to equal to positive infinity. So it's just getting bigger and bigger. Now let's do the same thing and see what happens for values close to 1 from the left. So we'll start with 0.9. Plugging that into our function, we'll get negative 10. Try 0.99, we get negative 100. 0.999, we get negative 1,000, and so on and so forth. So this tells us, this is negative 1,000. So this tells us that the limit of our function, as we're getting closer and closer to 1 from the left, is getting bigger and bigger negative. So it's approaching negative infinity. And then below here is the graph of our function. And what we have is that there's a vertical asymptote here. And graphically, we can see that this is the case that we're never actually going to hit this one here. We're never going to cross this vertical asymptote. We're just going to get closer and closer to positive infinity and negative infinity. All right. Let's take a look at this table here, kind of like a guideline. See that if we have a right-hand limit that is approaching infinity and our left-hand limit that's approaching negative infinity, the two-sided limit will not exist because they're approaching two different numbers. And then if we have the right hand and the left hand limit are equal to the same, to positive infinity, we'll get that our limit is equal to infinity. And similarly, if we got that the limit was negative infinity and negative infinity, then our two-sided limit would be negative infinity. So just like in our last section, a limit does exist if the left hand and right hand limits are equal, but if they are not, that's where we run into some trouble. All right, so let's let's look at some limits at infinity. So if our x values were to get bigger and bigger and approach infinity. So let's suppose p is a positive real number. Then we know that this exponent, x to the power p, increases as x increases. And another way of saying this is that there is no upper bound on the values of x to the power p. And symbolically, we will write this as the limit of x to the power p is equal to infinity as x goes to infinity. So as x gets bigger and bigger, our function gets bigger and bigger. And on the other hand, we do know that reciprocals of very large numbers are very small numbers. So in this case, if we were to have the function 1 over x to the p, we know that the limit as x gets bigger and bigger is going to actually just be equal to 0. And just to solidify this a little bit, let's look at our table. So let's say our p-value in this example is 2. And we were to plug in some numbers, I don't know, let's just get bigger and bigger. We were to plug in some numbers into x squared. We would get 2 squared, which is 4, 10 squared, which is 100, and 100 squared, which is 10,000. And if we were to repeat this, we see that this number is just getting bigger and bigger. Our output's just getting bigger and bigger. And so that's what this is saying here. And then looking at the reciprocal, let's do the same thing. Here f of x is equal to 1 over x squared. Now let's again just plug in the same numbers. Let's do 2, 10, and 100. So if we were to plug in 2 for x, we get 1 over 4. Then we were to plug in 10, we get 1 over 100, which is significantly smaller than 1 over 4. And if we were to plug in 100, we would get 1 over 10,000. So repeating this number is getting smaller and smaller and smaller and closer to 0. So that's what this means here. Okay, and then this graph here shows our f of x equals x squared and our 1 over x squared. So this is the behavior of these guys, and then this is symbolically what we would write as x gets closer and closer to infinity. All right, now for our function in this graph, we have this line here, y is equal to 0, and it's called the horizontal asymptote. And we're told that in general, this line will be a horizontal asymptote of our graph if our function approaches b, our line y is equal to b, as either x increases without bound or decreases without bound. So essentially, our line y equals b is a horizontal asymptote if, as we get closer and closer to negative or positive infinity, our limit is equal to that number b. Okay. So this next theorem, theorem 2, is the limits of power functions at infinity. So again, let's let p just be some positive real number, and k is going to be any real number except for 0. Then we have these 4 properties here. So if we have this function here, we have some number k over our x to the power p. We know that as we increase negatively, as we go to negative infinity, our limit is going to be equal to 0. We showed that here. And similarly, if we were to increase x in the positive direction, so go to positive infinity. And then properties 3 and 4 showcase the opposite. So pretty much what we saw here, that as we increase x and gets closer and closer to infinity, we get closer and closer to infinity. And this happens whether we approach negative infinity or positive infinity. And the limit will either be positive or negative infinity depending on what values we have for our k or our x. Okay, so let's look at a few examples. We're going to let our function p of x equal to this here, and we want to find the limit of our function as x approaches infinity and negative infinity. And so what we're going to do is rewrite our p of x in terms of these properties here. So I want to either have everything of this form or of this form, just so we can see if something's approaching 0 or infinity rather quickly. And we'll walk through this and it'll make a little more sense. So what we're going to do is, actually let's write this out. First, in order to get our terms in these forms, we'll factor out what's called the leading term. And our leading term is the term with the highest degree. So in this case, our leading term is the negative 4x to the power 4. Now, factoring this out, I'm not going to take out the negative. You can, if you want, you can have the negative x to the power 4 here, but I'm just not going to do that in this example. You'll end up with the same answer. But if we were to take out 4x to the power 4 from this, our first term just ends up being negative 1. Our second term is going to remain a positive, and off the top of our heads, it might be a little difficult to just pull out 4 times x to the power 4 from this. So what I'm going to do is first write it as this here, because we know definitely if we were to distribute this, then the 4x to the power 4's cancel, and we're left with 2x cubed, which is what we want. So I'm going to write this for each term just so we know exactly what is happening there, and then we can simplify it. So we have negative 1, and we have we have 2 over 4, so that's going to be 1 over 2 in the bottom, and then we have x to the 4 on the bottom and x cubed on the top, so those cancel and we're left with 1 more x on the bottom. And same for this next term, 3 over 4 doesn't reduce at all, so we still have 3 on the top and 4 on the bottom, and then we have x to the power 4 on the bottom and just 1x on top, so we're left with x cubed on the bottom. Okay, great. Now what we can do is take the limit as x goes to infinity of this guy here. And we know by theorem 2 here that if we were to take the limit of our function that looks like this, so some number over our x to the power p, then we get 0. And so that's exactly what we're going to look at here. We know that if we were to approach infinity, then this is going to approach 0, and this is going to approach 0. Again, because we have our reciprocals here, this number is just getting smaller and smaller as x gets bigger. I'm sorry, we are approaching infinity. Okay, so this tells us that this whole thing is pretty much equal to negative 1, right? Because the limit of negative 1 as x goes to infinity is just negative 1. And the reason we took the limit of just this guy here as x goes to infinity is because now we know that as we get closer and closer to infinity, our p of x is going to get closer and closer to just our 4x to the power 4 term here. All right, so this will get closer and closer to 4x to the power 4 times, and sorry, this is negative 1 because we got negative 1 up here. So this is getting closer and closer to negative 4x to the power 4. So this tells us that if we were to take the limit of negative 4x to the power 4 as x goes to infinity, what we're going to do is plug in an infinity for our x, just so we can see what's happening. And so we're saying -4 times infinity to the power 4. Well, we're just taking infinity times infinity times infinity times infinity. And so that's just going to be a really, really large number, which we write as infinity. Now, if we were to take -4 times infinity, or just 4 times infinity in general, we're again just going to get infinity. It's just a really, really large number that we're never actually going to get to. And so since we have a -4 up front, this tells us that we're going to negative infinity. And if we were to do the same thing as x gets closer and closer to negative infinity, we have -4 and then negative infinity to the power 4. And so again, this is just going to be negative infinity. All right, so this tells us that we do have a two-sided limit. As we approach negative and positive infinity for our function p of x, we get closer and closer to negative infinity. All right. Now we're going to, oh yes, here is a little blurb about our leading term here. In this example that we just did, we saw that the limits at infinity of our function were essentially just the same as the limits of the leading term. Right, so we really just looked at our leading term here, and we saw that the limits of our function were just equal to the limits for our leading term. Okay, and theorem 3, which we're about to go over, states that this is true for any polynomial of degree greater than or equal to 1. So that's what this is telling us. If we were to have a polynomial of this form here, and the limit of this polynomial as x goes to infinity is the same as the limit of the leading term of the polynomial as x goes to infinity, and that'll equal infinity or negative infinity. And same if x were to approach negative infinity. And the signs of our limits are going to be dependent on our a of n and our power. So we're going to look at this example from the book, the end behavior of a polynomial. So our polynomial is this here, this p of x. And so what we're doing is by theorem 3, we can just take the limit of the leading term here, which is the 3x cubed. And just like how we did in the last example, we can just plug infinity into our x here. So we get infinity cubed, which is just infinity. And then 3 times infinity is also just infinity. So that's why we get infinity here. And then if we were to do the same thing as x approach negative infinity, we again look at our leading term. The only difference here is that if we were to plug in negative infinity into this x here, we get negative infinity cubed. And we all know that a negative number cubed is equal to a negative number. And so that's why we get negative infinity here. Okay, so if we were to look at example B now, let's look at this polynomial. Again, if we want to take the limit of this polynomial as x goes to infinity, it's the same as taking the limit of the leading term as x goes to infinity. And remember, the leading term is the term with the highest power. So we have x to the power 4 here. And again, we can just plug in infinity into x here, and infinity to the power 4 is still just infinity. And then we have this negative 500 out here, so this makes this a negative infinity. And doing the same thing as x approaches negative infinity, we can look at our leading term and plug negative infinity into our x here. Negative infinity to the power 4 is positive infinity, but again, this negative out here in front of 500 makes this a negative infinity. All right, so that is how we would use theorem 3 to look at the limits of our polynomial functions at infinity. All right, now what we're going to do is look at an application. We're looking at an application of sales analysis. So if we were told the number of downloads, excuse me, D in millions of a new app T months after it is released is given by this function here. We want to find out what the limit of this function would be as t gets closer to infinity. So what we'll do first, again, is factor out the leading term. And since we're dealing with a rational function, we're going to do this from the numerator and the denominator. All right. So we end up with d of t is equal to 4t squared is the leading term in the numerator, and then 5t squared is the leading term in the denominator. So we're just ending up with 1 on the top. Then this needs to be distributed to our numerator, so that's just going to be a 1 there. 5t squared times 1 is just 5t, which is what we started with. And pulling out a 5t squared from this constant 70 here, we get 70 over 5t squared. And if we were to multiply this back out to each term, we would get our original denominator. All right. Then we can simplify this a little bit. We have t squared in the numerator and the denominator here, so those will cancel. And now let's take the limit of our d of t as t goes to infinity. So the first thing we'll do is we'll take the limit of this constant 4 over 5 on the outside, and then we can multiply that using our limit rules by the limit of this guy as t goes to infinity. All right. Now remember, if we have 70 over 5 times t squared, this number is going to get closer and closer to 0, right? As t goes to infinity, this number is getting smaller and smaller as we increase t. So this tells us, and also the limit of a constant is just going to be that constant. So we still have this 4 over 5 on the outside. And then the limit of this guy here is just going to be 1 over 1 plus 0, because this is getting, like we said, smaller and smaller as t goes to infinity. And so we just end up with 4 over 5 times 1, which is 4 over 5. All right. So that is our answer for that one. Now let's look at horizontal asymptotes. So we talked about vertical asymptotes. Now we gotta talk about horizontal asymptotes. And I know this is a lot, but bear with me. We'll start off by mentioning that since a rational function is the ratio of two polynomials, it's not going to be surprising that reciprocals of powers of x can be used to analyze the limits of our rational functions at infinity. So we'll start off with theorem 4. And this here says if we have a rational function here, then, so we have two polynomials, then the limit of this rational function as x goes to infinity is going to be the limit of our leading term. So this is going to be our leading term in our numerator over our leading term in our denominator. And similarly for x going to negative infinity. And so in these cases, there are three possible cases for these limits. And it's when m is less than n, m is equal to n, or m is greater than n. And so m and n are these guys here. And you don't really have to memorize these. When trying to find the horizontal asymptotes, you'll end up with one of these cases. But let's look at a few examples to illustrate this. So using we'll look at A first, and then using part A from our theorem 4, we know that the limit of this guy is going to be the limit of the leading terms, right, from the numerator and denominator. So what I mean by this is that the limit as x goes to infinity is going to be the limit of 4x cubed over 2x to the fourth as x goes to infinity. So we just have to look at the leading terms of both. All right, now this is pretty simple. Simplifying this, we get the limit of 2 over x as x goes to infinity. And then we know that as x gets bigger and bigger in the denominator here, this number is going to get closer and closer to 0. So this is equal to 0. And if you notice here, if m is less than n, and in our case it is, m is on the top, and so 3 is less than 4, then the limit is going to be equal to 0, and that is our horizontal asymptote. So our horizontal asymptote is the line y is equal to 0. Additionally, for this case, if m is less than n, then we're automatically told that the limit from the right is equal to the limit from the left. So we have a two-sided limit here, so we actually don't even need to check the limit as x approaches negative infinity. Okay, now let's do the same for b. We know that the limit of this function is going to be the same as if we were to just look at the limit of the leading terms in the numerator and denominator. And simplifying this, we get 5x over 2. And then in this case, we don't have a variable in our denominator. So we know that if we were to plug infinity here, or just get closer and closer to infinity, this number is going to get bigger and bigger. So our limit is equal to infinity. And in this case, our m is greater than our n value. So we're looking at part 3 of this theorem here. So if m is greater than n, then each limit will either be positive or negative infinity, depending on our parameters here. And this tells us that our function does not have a horizontal asymptote. So for this one, we would just write no horizontal asymptote. All right. And then we just have one more problem for this section. What we want to do is find all vertical and horizontal asymptotes of our function. So remember, for our vertical asymptotes, we want to see which values will make the denominator 0 here. So we'll just take, we got x squared minus 4. So we want to figure out which values will make that equal to 0. So solving for x, we get x squared is equal to 4. And then taking the square root of both sides, we get x is equal to positive 2 and negative 2. And then remember, we don't have a vertical asymptote if we are in indeterminate form. So we just want to make sure that if we were to plug in positive 2 and negative 2 into our function, we wouldn't get 0 over 0. And automatically, if we were to plug in 2 or positive 2 here, either way we get 4. And 4 minus 9 is not equal to 0. So this tells us that these are both vertical asymptotes. So we have one at x is equal to 2 and one at x is equal to negative 2. All right. Now for the horizontal asymptotes, we'll find our limits at infinity. So we know that the limit of our function as x goes to infinity, the same as looking at the limit of our leading terms here from our numerator and our denominator. And the leading term in both is just x squared. So this tells us that we're looking at the limit of just 1 as x goes to infinity, and we know that this is just going to be equal to 1. All right, so this tells us there's a horizontal asymptote at y is equal to 1, And you can check what happens as x goes to negative infinity as well, but either way, we're always just going to end up with a simplified version of 1. So yeah, this is our horizontal asymptote. And that is all for this section.